Hi, this is Paul Smith in Dr. Mosley's Biology 1081 class, and we're studying meiosis. And one of the questions we need to be able to answer is if we're given a set of pairs of alleles, how many different gametes can form from it? Uniquely different types of gametes can form from it. And the example you see on the screen is the one that we did in class, and the answer there happened to be four. But it wasn't four because there were four pairs of alleles. With that, with any particular pair of four alleles, you could get as few as one or as many as 16 different gametes from it. So deciding exactly what the right answer is kind of tricky. So I thought I'd put together a video to explain maybe a little bit more completely how to come up with the right answer. And I want to do it in two phases. First, I want to show you how to come up with all the possible combinations of them one at a time, and then you just count up how many you came up with, and that's the answer to the question. But then I also want to give you a simple formula for getting to the right answer very quickly. But I want to show you how to do it kind of the slow way first so that it's more obvious to you why the right answer is the right answer. So stick with me till the end and you'll get the short formula. So let's start simply. And that is with a case where there's four pairs of alleles and all of them are homozygous. In this case, there's three of them that are homozygous dominant and only one of them that's homozygous recessive. But it doesn't matter whether they're dominant or recessive. What matters is that all four of them are homozygous. They're the same. Okay, so let's figure out how many possible gametes could form from this. And the way a gamete forms, it's going to take one allele from the father or one from the mother, but it can't take both. It's going to have to take one or the other. So let's go through the first example. So for the P, since they're both the same, it's going to have to choose a dominant capital P. Well, and it's the same with the Y. It's homozygous. There's only a dominant form in this particular case, so it's going to have to be a big Y. For the R's, there's only little r's. It's homozygous recessive, so there's only going to be an option for a little r. And the T is going to have to be a big T because there's no other option. All right, so that is one option for one gamete from this particular set of four pairs of alleles. Now, are there any other possible combinations of those letters? And the answer is no, because all of them are homozygous. There's only one option for each of the letters, and this is it. So in this case, the answer is one. There's only one gamete that can form from this particular set of four pairs of alleles, and none of them are heterozygous. And I'm keeping track on the left of how many are heterozygous for a reason that will become clear later, but in this case, the answer is one. All right, let's make it a little bit more complicated, and let's change one of those pairs of alleles from homozygous to heterozygous. So now there's a dominant and a recessive option on the Y gene. Okay, so let's go through how many options are possible. Well, for the first one, the P has to be a capital P because there's no other option. We get to the Y's, and well, now we have two options, a dominant and a recessive. Well, we're going to use both of them eventually, but let's start with the dominant one. Didn't have to be, but let's just start with the one on the left. And then we go to the R's, it's got to be a little r because that's the only option. Let's go to the T's, it's got to be a big T because that's the only option. Okay, so that's one option for gametes. But there's another option as well because we know there's two options for Y. So let's go ahead and write down the lowercase, the recessive Y, for the second option. And what do the other letters have to be? Well, it still has to be a capital P because that's the only option. Still has to be a little r and a big T because those are the only options. So that's a second gamete that could form from this particular set of allele pairs. Are there any others? And the answer is no, because three of them are homozygous pairs, and only one of them is heterozygous, and so that's the only one with more than one option. So there's only two. So the answer in this case is two, and there's only one heterozygous pair. Right? So let's go on to the next one, make it a little bit more complicated. I'm going to change one more of them from homozygous to heterozygous. So in this case, the T is, I'm going to add a little t here instead of a big T. And I got the first two answers here just to make it go faster. Notice that these are the exact same two as we just came up with here, okay? And for the same reason. So if you need to go back and look at how we came up with those, it's the same answer. But now we have this little t here, which means we'll have really twice as many options because we had two options with only one t. Well, with a smaller t, well, now we have two more options. The third option will be the same as the first one, except instead of a big T, it'll be a little t. And the fourth option will be the same as the second option, big P, little y, little r. And instead of the big T, it'll be a little t. Okay? Now, notice that all the p's are still capital P because that's the only option, and all of the r's are recessive r's because that's the only option. But the y's, there's two options, and you'll notice that they show up. Half are going to be dominant, half are going to be recessive, and the t's are heterozygous, and so half of the gametes will have a dominant, half recessive, but these are the only four options you can come up with. And if you need to pause the video and convince yourself that there are no other combinations, do so. But the answer here in this case is going to be 4, and there are 2 heterozygous pairs. All right, let's go one more, and that'll be enough to see the pattern that's going to emerge. So here, and I've already got the answer there just to save time, but here I'm going to change one more homozygous pair to a heterozygous pair. So I'm going to change that little r to a big R. And it turns out in this case, there are 8 possible gametes that could form, but notice the first 4 are exactly the same as the 4 that we had before for the same reasons, okay? But the fact that we now have a big R means that we have 4 more options, because in the first 4, all the R's were little lowercase, recessive. But now, since we have a big R, that gives us 4 more options, the same as the first 4, but just with a big R instead of a little r. Okay, so that adds up to 8. So the total number possible here is 8, and there are 3 heterozygous pairs and only 1 homozygous pair. So let's look at the pattern that has just emerged. When we had no heterozygous pairs and they were all homozygous, the answer was there's only 1 gamete that can form. When we had 1 heterozygous pair, the answer was 2. When we had 2 heterozygous pairs, the answer was 4. And when we had 3 heterozygous pairs, it jumped up to 8. Right, now this pattern will continue. What you're seeing here is that it starts with 1 and it doubles after that. And anytime you have a pattern like that in numbers, you can come up with a formula to predict what each number in the sequence will be to make the answer easier. And that's why we were tracking the number of heterozygous pairs, because that's the number we'll use for the formula. So here is the formula that will predict these numbers. 2 to the nth power. That's it. That's the entire formula. 2 to the n. In this case, the n is the number of heterozygous pairs, not homozygous pairs and not total pairs of alleles, but the number of heterozygous pairs, and that's why we were tracking it. So the total number of gametes possible is going to be 2 to the power of n. All right, so let's look at the examples we did so far using the formula to see if it worked. All right, in the first one, we had 0 heterozygous pairs, so you put that 0 up here, 2 to the 0 power equals 1. If you don't remember that, look back at your high school algebra notes. Any number to the power of 0 equals 1. When we had 1 heterozygous pair, you put that here. 2 to the 1 to the power of 1 is just 2, and that turned out to be the right answer. 2 heterozygous pairs, so the formula is 2 to the 2nd power, or 2 squared, which equals 4, and that was the right answer. And when we had 3 heterozygous pairs, 2 to the 3rd power is 2 times 2 times 2, which is 8, and that was the right answer. And this pattern will continue no matter how many heterozygous pairs you have. So let's do one last quick example, and that is using the formula instead of marking up all of the different options and counting them. And it can even be a ridiculously complex problem, and we can still get the answer very, very simply. In this case, I doubt Dr. Mosley would ever give us one this complicated, but even if she did, we could answer it very easily. So in this case, there are 10 different pairs of alleles, and the question is how many uniquely different gametes could form from this. And if you didn't have the formula, it could take you hours to figure that out, but we can do it in just a few seconds, because all we have to do is count up the number of heterozygous pairs. So let's look at the first one. It happens to be heterozygous. The second one is not. The third one is, and the fourth one, and then this one, and this one, and this one. So it looks like 6 of the 10 are heterozygous, and the other 4 are homozygous. So the n here in this case is 6. 2 to the nth power, that would be 2 to the 6th. If you put that into your calculator and hit enter, you'll get the answer to be 64, and that turns out to be the right answer in this case, and you can use this formula with any of these problems. Good luck, and let me know if you have any questions.